There's something haunting about the night sky, not just its beauty, but its secrets. Picture this. You're staring up at a familiar patch of stars, tracing constellations you've known since childhood, when suddenly you realize something's missing. Entire clusters of stars, once blazing brightly, have vanished without a sound. No explosive farewells, no dazzling supernovas, just silence. This isn't science fiction. It's one of the most baffling mysteries in astronomy. Where do these massive star clusters go, and why do they disappear without leaving behind the cosmic fireworks we expect? The answers might rewrite everything we thought we knew about how stars live and die. For centuries, we've believed that the fate of a star was written in its size. The biggest ones were supposed to go out in a blaze of glory, collapsing into supernovas so bright they outshine entire galaxies. But the universe loves to surprise us. Astronomers have now spotted multiple cases where colossal star clusters, packed with stars that should have exploded, simply fade away. It's as if the universe has a hidden backdoor, a way for these giants to slip out unnoticed, and what's left behind is even stranger: dark voids, unexplained gravitational ripples, or perhaps something far more exotic lurking in the shadows. Could black holes be swallowing them whole? Is dark matter playing tricks on us? Or is there an entirely new cosmic phenomenon waiting to be discovered? This isn't just a puzzle for scientists, it's a story that changes how we see the cosmos. If stars can vanish without a trace, what else have we gotten wrong about the universe? Today, we're diving deep into the evidence, from telescopic ghost hunts to mind-bending theories that stretch the limits of physics. We'll explore how astronomers track these disappearing acts, why traditional models fail to explain them, and what bizarre objects might be taking their place. By the end, you'll see the night sky differently, not as a static painting, but as a dynamic, ever-changing mystery. So let's begin. The case of the missing stars is open, and the truth is stranger than fiction. The universe has a way of defying expectations, and nothing proves this more than the eerie disappearance of massive star clusters. These cosmic giants, packed with stars dozens of times heavier than our sun, don't just wink out of existence, they vanish without the fanfare we've come to expect. Normally, when a massive star dies, it goes out with a bang. A supernova so powerful it can outshine entire galaxies for weeks. But these clusters, they leave behind no such fireworks, no glowing debris, not even a whisper of their departure. It's as if they're slipping through a cosmic trapdoor, vanishing into the dark. So what's really happening? The key might lie in the crushing power of gravity. When stars in these clusters reach the end of their lives, their immense mass could be triggering a far stranger fate than a supernova. Instead of exploding outward, they might collapse inward so violently that they bypass the explosion entirely, forming black holes directly. Imagine a star so heavy that its own weight becomes a death sentence, folding space-time around it like a curtain closing on a stage. No light escapes. No shockwave ripples out, just silence. But here's where it gets even weirder. Some theories suggest these vanishing acts could be the work of dark matter, the invisible glue holding galaxies together. Could dark matter be pulling strings behind the scenes, nudging stars into early graves? Or perhaps the clusters are being shredded by rogue supermassive black holes lurking between galaxies, swallowing stars whole before they ever get a chance to shine one last time. The more we learn, the clearer it becomes. The universe has more tricks up its sleeve than we ever imagined, and the implications are staggering. If massive stars can disappear without a trace, it means our textbooks on stellar evolution are missing entire chapters. Every vanished cluster forces us to rethink the rules, not just about how stars die, but about what might be hiding in the shadows, waiting to be discovered. Stellar evolution has always been painted as a cosmic life cycle with clear rules, like a play where every star knows its final act. Take our Sun, for example. In about 5 billion years, it'll swell into a red giant, shed its outer layers, and fade into a dense, Earth-sized ember called a white dwarf. But for stars born with masses 20 times greater than our Sun, the script was supposed to be more dramatic. These colossal stars burn through their fuel at breakneck speeds, ending in a cataclysmic supernova, a spectacle so bright it can outshine an entire galaxy for weeks. Yet something's gone missing from this cosmic theater. Astronomers have spotted massive stars vanishing without delivering their promised final performance. It's as if the lead actor walked offstage mid-scene, leaving the audience in stunned silence. The most plausible explanation: these stars might be skipping the supernova entirely, collapsing so violently under their own weight that they form black holes without the usual fireworks. Think of it like a building imploding inward instead of exploding outward. No debris, no shockwave, just an eerie absence where something monumental once stood. This isn't just theoretical. In 2015, astronomers watched a giant star in the galaxy NGC 3125 simply disappear. No explosion, no fading glow. One day it was there, shining with the energy of millions of suns. The next, its light had vanished, the best explanation. The star's core collapsed straight into a black hole, swallowing its own death cry before it could reach us. It's a cosmic magic trick with universe-altering implications. If stars can vanish this way, it means black holes might be forming more frequently and more quietly than we ever imagined. But here's the twist: not all vanishing acts fit this mold. Some clusters disappear too quickly, too cleanly, for even a silent black hole collapse to explain. That's led scientists to wilder possibilities, like stars being shredded by rogue black holes or unraveled by dark matter's invisible pull. Each theory is a reminder that the universe still holds cards close to its chest. The more we learn, the clearer it becomes. The death of a star isn't just about size or gravity. It's a mystery with more endings than we ever dreamed. Black holes might be the universe's ultimate illusionist, swallowing stars whole without leaving a single clue behind. Picture a cosmic vacuum cleaner so powerful that not even light can escape its pull. When a massive star collapses directly into a black hole, it doesn't just fade away quietly. It's erased from the cosmic record, as if it never existed. No fiery explosion, no lingering glow, just an absence where a star once burned. This could explain why astronomers sometimes train their telescopes on a cluster of stars, only to find gaps in the sky where brilliant giants should be. The terrifying elegance of black holes is that they don't just hide stars, they hide themselves. Unless a black hole is actively devouring gas or dust, creating a glowing ring of superheated material called an accretion disk, it's practically invisible. That means entire generations of stars could be vanishing into these gravitational pits without us ever seeing it happen. But in the last decade, we've gotten a new way to detect their shadowy presence: gravitational waves. These ripples in space-time, first detected in 2015 by LIGO, are like cosmic footprints, proof of black holes moving, merging, and reshaping the fabric of reality itself. Some of the most compelling evidence comes from mergers between black holes far heavier than our models predicted. When two of these invisible giants collide, the resulting gravitational waves carry a telltale signature, one that suggests black holes might be forming more frequently and in more ways than we ever thought. Could these unseen mergers be the final act for entire star clusters? It's a chilling possibility. Imagine a swarm of stars, each silently collapsing into black holes, then slowly spiraling toward one another over millions of years until, silently, invisibly, they merge and vanish without a trace. Yet even this explanation doesn't fit every case. Some disappearing clusters leave behind no gravitational wave signatures, no X-ray echoes, no hints of their fate. That's forced scientists to consider even stranger ideas, like primordial black holes, forged in the chaos of the early universe, or dark stars, hypothetical objects powered by dark matter annihilation. The deeper we dig, the more we realize the cosmos might be teeming with invisible predators, rewriting the rules of stellar life and death right under our noses. And the scariest part, we're only just learning how to look for them. Dark matter might be the universe's ultimate puppet master, tugging at the strings of star clusters in ways we're only beginning to understand. Imagine an invisible force far heavier than all the stars and galaxies we can see, silently shaping their fate. This mysterious substance makes up roughly 85% of the universe's mass, yet it doesn't emit, absorb, or reflect light. It's like a ghostly hand bending space and time without leaving fingerprints, and some researchers think it could be the key to why massive star clusters vanish without a trace. Here's how it might work. Dark matter isn't spread evenly. It clumps into vast, invisible halos around galaxies, creating gravitational hotspots. If a star cluster drifts too close to one of these dense patches, the extra tug could destabilize its delicate balance. Stars might get ripped apart or flung into the void, their light fading as they're pulled into darkness. Even more unsettling, dark matter particles could interact with stars in ways we don't fully grasp, perhaps transferring energy that speeds up their collapse. Picture a candle melting unnaturally fast under an unseen flame. There's tantalizing evidence for this idea. In some galaxies, star clusters near the edges, where dark matter is thought to pile up, seem to dissolve faster than those near the center. It's as if something's erasing them from the outside in. And in simulations, when scientists add dark matter's gravitational influence, star clusters behave erratically, scattering or collapsing in ways that mirror real-world disappearances. But the wildest possibility, dark matter itself might form exotic objects we've never detected. Some theories suggest it could coalesce into dark stars, invisible behemoths fueled by dark matter annihilation rather than nuclear fusion. If these exist, they might lurk at the hearts of vanishing clusters, swallowing ordinary stars like shadows consuming light. Or perhaps dark matter particles are crashing into stars, injecting enough energy to trigger silent implosions. The challenge is proving any of this. Dark matter doesn't just hide its actions, it hides itself. We only know it's there because of its gravitational grip on galaxies. To catch it in the act, astronomers are hunting for oddities, star clusters that break the rules, galaxies with unexplained gaps, or strange heat signatures where dark matter might be at work. Every disappearance is a clue, and every clue leads us deeper into the dark. One thing's certain: if dark matter is behind these vanishing acts, it's rewriting the rules of astrophysics. We're not just searching for missing stars, we're piecing together the invisible architecture of the cosmos itself. And with every discovery, the universe feels a little stranger, a little more alive with secrets. Failed supernovas might be the universe's quietest cosmic disappearing act, a stellar death so abrupt, even the star's final scream is swallowed by the darkness. Normally, when a massive star reaches the end of its life, the battle between gravity and nuclear fusion reaches a fever pitch. The core collapses, then rebounds in a shockwave so powerful it blasts the star's outer layers into space in a spectacular supernova. But sometimes gravity wins too completely. Instead of that explosive rebound, the core keeps collapsing, folding in on itself until it crosses the point of no return, forming a black hole without the fireworks. Take the case of N6942, a red supergiant 25 times more massive than our Sun. Astronomers watched it for years, expecting it to erupt in a supernova that would light up our skies. Then, in 2015, it simply blinked out. No explosion, no fading embers, just darkness where a titanic star once burned. The most likely explanation: a failed supernova. The star's core, dense and heavy, may have collapsed straight into a black hole, its outer layers falling inward like a curtain dropping at the end of a play. No encore, no standing ovation, just silence. What makes these events so unsettling is how they defy the script we've written for stellar deaths. A supernova isn't just an ending, it's a cosmic recycling program. The explosion scatters heavy elements, carbon, oxygen, iron across space, seeding future generations of stars and planets. But a failed supernova locks those materials away inside a black hole's event horizon, as if the universe hit a cosmic delete button. That means entire chapters of cosmic history could be vanishing without a trace, stolen by gravity before they ever get a chance to contribute to the story. And the implications ripple outward. If failed supernovas are more common than we thought, it could explain why we've underestimated the number of black holes in the universe. Surveys of distant galaxies keep turning up missing red supergiant stars that should have exploded but instead left behind ghostly voids. Each one is a clue, a silent witness to a process we're only beginning to understand. Yet even this explanation isn't perfect. Some disappearing stars don't fit the profile for a failed supernova. They're too small, too stable, or vanish too quickly. That's led scientists to wilder theories, like stars being shredded by rogue black holes or unraveled by quantum effects we haven't discovered yet. The deeper we look, the clearer it becomes. The universe has more ways to erase a star than we ever imagined. And every disappearance forces us to rethink what we know about life, death, and the invisible forces rewriting the rules. Runaway stars are the cosmic equivalent of fugitives blazing across the galaxy at unimaginable speeds, leaving their homes behind without a backward glance. These stellar escape artists don't just wander off. They're catapulted into the void by gravitational forces so intense they can reach velocities topping 1,000,000 miles per hour. Picture a game of cosmic pinball where stars ricochet off one another or get slingshotted by the gravitational pull of a passing black hole, flung into the darkness like marbles launched from a child's hand. But here's the twist. While runaway stars explain why individual stars vanish from clusters, they might not account for entire groups dissolving without a trace. Take the case of the star Zeta Ophiuchi, a blue giant racing through space at nearly 67,000 miles per hour. Astronomers traced its path back to a cluster near the center of our galaxy, where a close encounter with a binary star system likely hurled it into the void. Yet while Zeta Ophiuchi's story is dramatic, it's still just one star, not an entire cluster's worth. The real mystery lies in whether gravitational chaos could scatter a whole group of stars so efficiently that they appear to evaporate. Some simulations suggest it's possible. In densely packed clusters, especially those near galactic centers, stars engage in a relentless gravitational tug of war. Close encounters can fling multiple stars outward in opposite directions, like sparks from a firework. Over time, this could leave the cluster so depleted it seems to vanish, not because the stars died, but because they were exiled. Yet even this theory has gaps. Runaway stars leave trails, ionized gas, bow shocks, and telltale velocity signatures that astronomers can track. If entire clusters were disintegrating this way, we'd expect to see more of these cosmic breadcrumbs. Instead, some clusters fade uniformly, as if erased by an unseen hand. That's led scientists to suspect a combination of forces at work: runaway stars thinning the herd, while black holes, dark matter, or failed supernovas clean up the rest. The more we study these disappearing acts, the clearer it becomes that the universe operates like a grand stage with multiple trapdoors. Stars don't just die, they escape, collapse, or get swallowed. And every time we think we've figured out the script, the cosmos rewrites it. Globular clusters are like cosmic time capsules packed with stars nearly as old as the universe itself, shimmering in tight, symmetrical spheres. These ancient gatherings can contain hundreds of thousands, even millions, of stars crammed into a space just a few light years across. To stand on a planet inside one would mean a night sky so crowded with stars, there'd be no true darkness. Yet for all their brilliance, these clusters are slowly unraveling, their stars slipping away like sand through an hourglass. The question isn't just why, it's whether their fading is a natural cosmic rhythm or the work of unseen forces tugging at the seams. Take Omega Centauri, the Milky Way's largest globular cluster. Through telescopes, it looks like a snow globe of stars, a perfect sphere glittering with stellar giants. But zoom in, and you'll notice gaps, regions where stars are mysteriously sparse. Over billions of years, gravitational interactions between stars have flung some outward, sending them careening into interstellar space like marbles spilled from a jar. This process, called evaporation, is inevitable in dense clusters. Stars swing past one another in a relentless dance, and every close encounter can slingshot one member of the pair outward, never to return. But here's the puzzle. Some clusters are dissolving faster than physics predicts. Take Palomar 5, a faint, wispy cluster on the outskirts of our galaxy. It's so stretched out, it resembles a stellar stream more than a sphere. Conventional models suggest it should have taken billions of years to reach this state, yet its stars are dispersing at a rate that hints at outside interference. Could dark matter be tugging at its edges, or is the cluster's own gravity warped by an unseen black hole lurking at its core? The strangest clue comes from what's not there. In many globular clusters, the heaviest stars, the ones that should have sunk to the center like rocks in water, are missing. It's as if something scooped them out, leaving behind a lighter, more fragile skeleton. One theory points to intermediate mass black holes, cosmic middleweights that could lurk in cluster cores, swallowing massive stars before they ever reach old age. Another suggests that dark matter, if it's woven through these clusters, could be accelerating their decay like an invisible solvent breaking down a celestial structure. Yet even these explanations feel incomplete. Some clusters vanish unevenly, with stars peeling away in clumps rather than drifting off one by one. That's led astronomers to suspect tidal forces, the gravitational tug of war between a cluster and its host galaxy. As globular clusters orbit, the galaxy's gravity stretches them, stripping stars away in waves. It's like a cosmic game of keep away, where the losers are stars flung into the void. The implications ripple far beyond these clusters. If they're disappearing faster than expected, it means the universe might be erasing its oldest stellar communities before we've fully decoded their secrets. These clusters are living records of the early cosmos, holding clues about how the first stars and galaxies formed. Every vanished star is a lost page in that history. And as we watch more clusters fade, we're forced to wonder, are we witnessing a natural endgame, or is the universe playing a trick we've yet to understand? Between the well-known extremes of stellar black holes and their supermassive cousins lurks a cosmic middleweight class that could rewrite the rules of stellar disappearance, intermediate mass black holes. Imagine an object hundreds or thousands of times heavier than our Sun, yet dwarfed by the supermassive giants anchoring galaxies. These enigmatic entities don't form like typical stellar black holes born from collapsing stars. Instead, they might emerge through a sinister process, smaller black holes merging over eons in dense star clusters, growing silently like shadows pooling in a cosmic corner. Or perhaps they're forged in rare, apocalyptic collapses, super-sized stars imploding directly into black holes far heavier than physics should allow. Their very existence was theoretical until recent breakthroughs. In 2020, astronomers spotted gravitational waves from a collision so bizarre it defied expectations. A black hole 140 times the Sun's mass devouring a lighter counterpart. This wasn't just unusual, it was a smoking gun. The heavier black hole fit no known category, too massive for a stellar collapse yet too small for a supermassive beast. Suddenly, the hunt was on. Where else might these gravitational ghosts be hiding? Star clusters, especially globular ones, became prime suspects. Picture a crowded stellar dance floor where black holes, nudged by gravity, sink to the center like stones in water. Over time, they merge, grow, and start feeding. Here's where the vanishing acts begin. An intermediate mass black hole in a cluster wouldn't just lurk, it would dominate. Stars straying too close would be torn apart in tidal disruption events, their light swallowed before it could reach us. Others might be flung into the void by gravitational slingshots, thinning the cluster like a sieve. Unlike supermassive black holes, which announce their presence with blazing accretion disks, these middleweights could operate in stealth mode. No fireworks, no warning, just stars winking out one by one. The evidence is mounting. In the Cluster 47 Tucani, astronomers found stars orbiting nothing. Their path suggested an invisible object 4,000 solar masses tugging at them, a textbook intermediate black hole candidate. Nearby, in the cluster Messier 15, similar stellar orbits hinted at something equally massive lurking in the dark. If confirmed, these hidden predators could explain why some clusters dissolve faster than models predict, their stars vanishing as if plucked by an unseen hand. But the implications stretch further. If intermediate black holes are common, they might be the missing link in cosmic evolution seeds that grow into supermassive monsters by devouring clusters whole. Or perhaps they're cosmic nomads ejected from clusters during mergers, wandering the galaxy as invisible wrecking balls. Every discovery peels back another layer, revealing a universe far more dynamic and far more dangerous than we ever imagined. The night sky's quietest disappearances might not be accidents. They could be signatures of something lurking in the dark, rewriting the rules of stellar life and death one silent meal at a time. Gravitational waves are like cosmic whispers, ripples in space-time so faint we've only just learned to listen. These subtle tremors, first detected in 2015, carry secrets from some of the universe's most violent events: black holes colliding, neutron stars spiraling into oblivion, and perhaps even the silent deaths of stars that vanished without a trace. Among the hundreds of gravitational wave signals we've captured, a few stand out not for their loudness but for their strangeness. Some mergers involve black holes far heavier than any single star should produce, hinting at a dark possibility that massive stars might be collapsing directly into black holes, skipping their explosive final act entirely. Picture two black holes, each 30 times the mass of our Sun, locked in a fatal dance. According to traditional stellar models, stars that massive should leave behind bright supernova remnants, not invisible ghosts. Yet here they are, merging in the darkness with no stellar fireworks to mark their origins. The most compelling explanation: these black holes were born not from explosions, but from implosions, stars so massive their cores crumpled under their own weight, bypassing the supernova stage altogether. It's as if the universe hit a cosmic mute button, swallowing their deaths whole. The implications are staggering. If gravitational waves reveal that silent collapses are common, it would mean we've vastly underestimated how many black holes lurk in the cosmos. Surveys of distant galaxies already show gaps where massive red supergiants should be stars that vanished without the expected supernova fanfare. Gravitational wave astronomy could finally connect these missing stars to the black holes they likely became. Every unusual merger detected adds another piece to the puzzle, suggesting a hidden population of stars that slip away unnoticed, their fates recorded only in the faintest tremors of space-time. But the real breakthrough lies ahead. Future observatories like the space-based LISA mission set to launch in the 2030s will detect lower-frequency gravitational waves, ones that could reveal slower, quieter mergers happening over months or years. These signals might catch black holes forming in real time, offering a front-row seat to silent stellar collapses. Other detectors, like Einstein Telescope, will listen for fainter ripples from smaller black holes, potentially uncovering entire populations of these stealthy objects. What's most thrilling is how little we still know. Some gravitational wave events defy all expectations, like mergers in empty stretches of space where no stars should exist, or black holes spinning at impossible speeds. These outliers hint at even wilder possibilities: primordial black holes forged in the Big Bang's chaos, or stars warped by dark matter into shapes we don't yet understand. With every new detection, the universe reminds us the rules we've written are just rough drafts, and the truth is far stranger than we've dared to imagine. The next time you look up at the night sky, remember some of its brightest stars might already be gone, their light a lingering echo of objects that collapsed silently into the dark. And thanks to gravitational waves, we're finally learning to hear their untold stories. Neutron stars are the universe's silent survivors, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Born from the explosive deaths of stars not quite massive enough to form black holes, these cosmic relics pack more mass than our Sun into a sphere no wider than a city. Yet despite their staggering density, they're among the faintest objects in the cosmos, emitting barely a whisper of light. This eerie combination, extreme mass cloaked in near invisibility, makes them prime suspects in the mystery of vanishing star clusters. Could these ghostly remnants be hiding in plain sight, masquerading as empty patches of sky? Take the case of the star cluster Westerlund 1. Packed with hundreds of massive stars, it should, by all rights, host a graveyard of neutron stars left behind after countless supernova. Yet when astronomers scanned the cluster with X-ray telescopes, they found only a handful of these faint objects. The rest were missing, as if swallowed by the void. One explanation: neutron stars born from supernova often get a kick from asymmetrical explosions, launching them into space at speeds topping 600 miles per second. Over millennia, these runaway corpses could flee their birth clusters entirely, leaving behind no trace but gravity's faint tug. But there's another twist: some neutron stars might be hiding in plain sight. When a neutron star first forms, it's a pulsar, a rapidly spinning beacon emitting beams of radiation like a cosmic lighthouse. But pulsars don't shine forever. After millions of years, their rotations slow, their beams dim, and they fade into obscurity as dead neutron stars. These dark cinders, no longer pulsing, become nearly impossible to detect unless they're actively feeding on nearby gas. In a crowded star cluster, such silent objects could lurk undetected for eons, their presence betrayed only by subtle gravitational effects on neighboring stars. The most tantalizing clue comes from globular clusters like Terzan 5, where astronomers have spotted neutron stars in binary systems. These undead stars siphon material from their companions, glowing faintly in X-rays, yet even these detectable ones are far fewer than expected. Where are the rest? Some might have drifted into isolation, their faint thermal emissions lost in the cosmic background. Others could have collided and merged, forming heavier neutron stars or even black holes in processes too quiet for our telescopes to catch. The implications stretch beyond missing stars. If neutron stars are vanishing from clusters at unexpected rates, it could mean we've misunderstood their formation or evolution. Perhaps supernova kicks are stronger than models predict, or maybe dark matter interacts with neutron stars in ways we can't yet see. Every undetected neutron star is a silent witness to physics operating in extremes, a reminder that even the universe's faintest ghosts have stories to tell, if only we learn how to listen. Cosmic voids are the universe's empty rooms, vast stretches of space where galaxies and star clusters should be, but aren't. Picture a sponge soaked in water. The bubbles trapped inside are like these voids, dark pockets surrounded by the glowing filaments of the cosmic web. But unlike sponge bubbles, these voids aren't just empty. They're actively growing, stretching wider as the universe expands, leaving astronomers to wonder, did they always lack stars, or did something tear them away? One of the most baffling examples is the Boötes void, a spherical region over 300 million light-years across containing only a handful of galaxies. Based on our understanding of cosmic structure, it should host thousands. So where did everything go? One theory points to dark energy, the mysterious force accelerating the universe's expansion. As space stretches, the gravitational bonds holding star clusters together might weaken, allowing them to drift apart like leaves on a receding tide. Over billions of years, these clusters could dissolve into the void, their stars scattered too thinly to detect. But there's a darker possibility. Larger cosmic structures might be consuming them. Galaxies don't just sit still, they move, pulled by the gravity of nearby superclusters or unseen concentrations of dark matter. Imagine a star cluster drifting too close to a massive galaxy cluster like Coma or Virgo. The tidal forces would shred it, stripping stars away like petals in a storm. Some might get absorbed into larger galaxies, while others could be flung into the void, left to wander alone. The strangest clue comes from the edges of these voids, where astronomers have spotted ghost galaxies, dim, diffuse collections of stars that look like the remnants of clusters torn apart. These phantoms, like the galaxy NGC 5474, hover on the boundary between void and structure, their stars stretched into long, faint streams. It's as if they're the last survivors of a massacre, their companions swallowed by the growing dark. Yet even these eerie remnants don't explain everything. Some voids are too empty, too clean, for even tidal forces to account for. That's led scientists to consider wilder ideas like primordial black holes, formed in the universe's first moments, lurking in these voids, devouring anything that ventures too close. Or perhaps dark matter isn't just clumping around galaxies, but also carving out these empty regions, pushing stars and gas aside like an invisible plow. The unsettling truth is this: cosmic voids might not just be where stars vanish, they could be where the universe's expansion writes its own rules. As dark energy accelerates, these voids will grow, their emptiness spreading like cracks in ice. The stars we see today, the clusters we study, might one day be lost to these expanding gulfs, their light stretched too faint to follow. Every void is a reminder that the cosmos isn't just evolving, it's erasing itself piece by piece, and we're only just beginning to read the signs. Tidal disruption events are the cosmic equivalent of a star's worst nightmare, a black hole's gravitational grip stretching, squeezing, and ultimately tearing it apart. Imagine a star drifting too close to one of these invisible predators. At first, nothing seems amiss, but as it crosses the point of no return, the black hole's tidal forces overpower the star's own gravity, elongating it like taffy in a process called spaghettification. The star's outer layers are ripped away, swirling into a superheated disk around the black hole and glowing brightly enough to outshine entire galaxies for months. These violent episodes should be impossible to miss. So why do some star clusters seem to lose members without a trace, leaving no flare behind? One possibility is that not all tidal disruptions are created equal. A star shredded by a supermassive black hole, like those at galactic centers, produces a spectacular flare, as seen in events like a SRSSN 15LH. But smaller black holes, especially intermediate mass ones lurking in star clusters, might not pack the same punch. Their tidal forces could strip a star apart more slowly, like peeling an onion layer by layer, resulting in a dimmer, longer-lasting signal that blends into the cluster's background glow. Or worse, if the black hole is particularly greedy, it might swallow the star's debris so quickly that little light escapes at all. Then there's the angle of perspective. A tidal disruption event's brightness depends heavily on our viewing angle. If we're looking edge-on at the accretion disk, the whirlpool of stellar debris circling the black hole, much of its light could be obscured by dust or simply beamed away from us. It's like trying to spot a lighthouse from behind. Unless the beam swings our way, we'd never know it was there. Some disruptions might even be dark, their energy channeled into powerful jets shooting out perpendicular to the disk, invisible to telescopes not aligned with their path. But the most intriguing explanation flips the script entirely. What if some stars aren't being torn apart, but are being swallowed whole? For smaller stars venturing too close to a sufficiently massive black hole, the event horizon might engulf them before tidal forces can rip them to shreds. No violent stretching, no glowing debris disk, just a star slipping silently into the abyss. This scenario, though rare, could explain why some clusters lose stars without the usual fireworks. Yet even this doesn't account for every disappearance. Some clusters show gaps where multiple stars have vanished in quick succession, a pattern that doesn't match the randomness of tidal disruptions. That's led astronomers to suspect more exotic culprits, like rogue black holes barreling through clusters, or dark matter interactions accelerating stellar decay. The truth might lie in a combination of these forces, a cosmic perfect storm where stars don't just die, but are erased from existence by the universe's most extreme phenomena. Every missing star is a puzzle, and every unexplained void in a cluster is a reminder. The cosmos doesn't always play by the rules we've written. Sometimes the most dramatic endings leave no trace at all. There's a glaring absence in our cosmic records, a silent discrepancy that's kept astronomers up at night. The universe's most massive stars, the ones that should end their lives in the most spectacular explosions imaginable, are vanishing without fulfilling their fiery destiny. Supernovas from these giants should be lighting up our telescopes like cosmic fireworks, yet the numbers don't add up. Where are all the missing explosions? The answer might lie in one of the most extreme acts a star can perform: a silent, sudden collapse into oblivion, skipping the supernova stage entirely and becoming a black hole without so much as a flicker of farewell. Consider the case of the red supergiant N6942, a star 25 times heavier than our Sun. For years, astronomers monitored it, waiting for the inevitable supernova, a blast so bright it would have been visible even in amateur telescopes. Then in 2015, it simply dimmed out of existence. No explosion, no shockwave, no telltale glow of expanding debris, just darkness. The leading explanation, the star's core, under its own crushing weight, collapsed directly into a black hole, its outer layers falling inward like a house swallowed by a sinkhole. No explosion, no warning, just a quiet exit from the cosmic stage. This phenomenon, called direct collapse, challenges everything we thought we knew about stellar deaths. Normally, when a massive star runs out of fuel, its core collapses until the pressure triggers a rebound, a shockwave that blasts the star's outer layers into space in a supernova. But if the core is too massive, that rebound might never happen. Instead, the collapse continues unchecked, the star's entire mass funneling into a singularity so dense not even light can escape. It's the ultimate cosmic vanishing act. The evidence isn't just anecdotal. Surveys of nearby galaxies reveal a startling shortage of supernovas from stars above a certain mass threshold. Statistically, we should be seeing far more of these explosions than we actually detect. The discrepancy suggests that up to 30% of the most massive stars might be skipping the supernova stage altogether, opting instead for a silent collapse. Computer simulations support this idea when models account for stars with cores above a critical mass. They predict a significant fraction will implode directly into black holes, their deaths marked only by a subtle dimming as their outer layers are consumed. But proving this theory is like trying to catch a shadow. Black holes born from direct collapse leave no luminous debris, no radioactive isotopes scattered into space, the usual fingerprints of a supernova. The only clues might be gravitational waves, the faint ripples in space-time from the moment of collapse. Future observatories like the Einstein telescope could detect these signals, offering the first direct evidence of stars slipping silently into the dark. Yet even this explanation doesn't cover all the gaps. Some missing supernovas involve stars that aren't quite massive enough for direct collapse, hinting at other mechanisms at play. Could interactions with binary companions trigger premature implosions, or are dark matter particles colliding with stellar cores, hastening their collapse in ways we haven't yet imagined? Every unanswered question is a reminder. The universe's most dramatic exits might be the ones we never see coming. The night sky's quietest disappearances aren't just cosmic curiosities, they're rewriting the rules of stellar life and death. If stars can vanish without a trace, what other chapters of astrophysics are waiting to be torn out and rewritten? The hunt for these ghostly collapses is more than a puzzle. It's a window into the universe's best-kept secrets. Supercomputers have become the ultimate cosmic detectives, running simulations so complex they can recreate the life and death of entire star clusters down to the finest detail. These digital laboratories let astronomers test theories that would take billions of years to unfold in nature, like watching a star cluster evaporate in fast forward. One of the most startling revelations: under the right conditions, massive stars don't just die quietly, they can disappear without leaving behind a single clue. Take the simulations run by teams at the University of California and the Max Planck Institute. They modeled dense star clusters where gravitational chaos reigns, stars whipping past each other at dizzying speeds. In scenario after scenario, the heaviest stars, those 20 times the mass of our Sun or more, met a fate that defied expectations. Instead of exploding in supernovas, their cores collapsed so abruptly that the outer layers simply fell inward, vanishing into black holes like water down a drain. No shockwave, no debris field, just an empty spot where a star once burned. But here's the catch. While these simulations explain how stars might vanish, matching them to real-world observations is like trying to solve a puzzle with half the pieces missing. For every cluster where stars disappear too quickly, like Palomar 5, there's another where they linger far longer than models predict. Some of this mismatch comes from the sheer complexity of star clusters, each one a swirling dance of gravity, radiation, and magnetic fields. Even the most advanced simulations can't account for every variable, like rogue black holes wandering through or dark matter's invisible pull. The most intriguing discrepancies come from globular clusters, those ancient stellar cities orbiting our galaxy. Simulations suggest their densest regions should be factories for black hole formation, with massive stars collapsing silently in droves. Yet when astronomers scan these areas with X-ray and radio telescopes, they find far fewer black holes than expected. Where did they go? One theory is that black holes, once formed, get kicked out of the cluster entirely. When two black holes merge, the gravitational waves they emit can launch the resulting heavier black hole like a rocket, ejecting it into intergalactic space. Other simulations show black holes sinking to the cluster's core, merging into a single intermediate mass monster that devours stars from the inside out. The stakes are higher than just solving a cosmic mystery. If simulations consistently overpredict how many black holes we should see, it might mean stars are vanishing in ways we haven't even coded into the models yet. Maybe dark matter particles are colliding with stellar cores, hastening their collapse. Or perhaps quantum effects at extreme densities allow stars to implode faster than physics currently allows. Every mismatch between simulation and observation is a breadcrumb leading to new physics, a hint that the universe's rulebook still has pages we haven't read. What's clear is this: the night sky isn't just a static backdrop. It's a dynamic, ever-changing arena where stars live, die, and sometimes slip away without saying goodbye. And with every upgrade to our supercomputers, every new algorithm that accounts for dark matter or magnetic fields, we get closer to catching these cosmic fugitives in the act. The simulations aren't just recreating the universe as we know it, they're revealing the one we never saw coming. Star clusters exist in a constant tug of war between gravity and chaos. Picture a crowded dance floor where every star moves to its own rhythm, occasionally brushing past another, exchanging energy in a celestial game of gravitational billiards. Over time, these subtle interactions add up. Some stars gain momentum, flinging them toward the cluster's outer edges, while others sink deeper into the heart of the group. It's a delicate equilibrium, one that can unravel over millions of years as the fastest stars break free entirely, drifting into the void like embers scattered by the wind. But here's the puzzle: some clusters seem to dissolve far faster than this natural process should allow. Take the Hyades, a nearby open cluster in the Taurus constellation. Its stars are dispersing at a rate that suggests something more than just internal dynamics is at work. Could unseen forces like dark matter's gravitational tides or an encounter with a massive gas cloud be accelerating its demise? Or consider the case of the globular cluster Palomar 5, stretched into a long, shimmering stream of stars as if pulled apart by invisible hands. Traditional models of cluster evaporation can't fully explain its extreme deformation, hinting at interference from an external player. The Milky Way itself might be complicit. As star clusters orbit our galaxy, they pass through regions of varying gravitational intensity, spiral arms, dense gas clouds, even other clusters. Each encounter leaves a mark, stripping away stars like fruit shaken from a tree. Simulations show that a single close flyby with a massive object, like the Sagittarius dwarf galaxy, could rip hundreds of stars from a cluster in one go. And then there's the galaxy's tidal field, the cumulative pull of billions of stars and dark matter, which stretches clusters like taffy as they swing around the galactic center. Yet even these explanations fall short for some vanishing acts. Certain clusters show gaps too abrupt, too symmetrical, to be the work of gradual dispersal. That's led researchers to wilder theories, like clusters plowing through clumps of dark matter, their stars destabilized by interactions we can't yet detect. Others propose that intermediate mass black holes, lurking undetected in cluster cores, are acting like cosmic wrecking balls, flinging stars outward with each gravitational swing by. The truth might lie in a combination of these forces, a cosmic conspiracy where internal dynamics and external threats team up to erase clusters faster than we ever imagined. Every disappearing star cluster is a reminder the universe doesn't just fade away quietly. Sometimes it vanishes in plain sight, leaving behind only questions and the faintest gravitational echoes. The James Webb Space Telescope is rewriting the cosmic rulebook, peeling back layers of dust and time with its unparalleled infrared gaze. Unlike Hubble, which sees mostly visible light, Webb's instruments detect the faint heat signatures of objects too cold or obscured for other telescopes, like the dim afterglow of vanished stars or the hidden cradles where new ones form. Already, its early observations have turned up baffling anomalies. In the Carina Nebula, a star-forming region teeming with young stellar giants, Webb spotted strange voids where massive stars should be. No debris, no shockwaves, just empty pockets defying explanation. Then there's the case of Messier 92, a globular cluster so ancient it formed when the universe was a fraction of its current age. Webb's sharp infrared vision revealed gaps in its stellar population, as if something had plucked stars from its core like berries from a bush. One theory suggests these missing stars collapsed into black holes long ago, their gravity subtly warping the orbits of nearby survivors, a ghostly fingerprint Webb can now trace. Other clusters show similar disturbances, their outermost stars stretched into streamers, hinting at close encounters with invisible mass. Could dark matter be the culprit? Or are we seeing the aftermath of black hole mergers, events so violent they eject stars like shrapnel? The most tantalizing clues come from Webb's deep field images, capturing light from the universe's infancy. In these snapshots, some early galaxies appear oddly lopsided, their stars unevenly distributed. One explanation: their central star clusters might have already evaporated, their brightest members vanished into black holes or torn away by tidal forces. If confirmed, it would mean the processes erasing clusters today were even more rampant in the ancient universe, a time when conditions were hotter, denser, and far more extreme. But Webb's greatest contribution might be catching a disappearance in real time. In 2023, it monitored a massive star in the galaxy NGC 6946, watching as it dimmed erratically before fading entirely. No supernova accompanied its death, just a flicker, then darkness. Astronomers are still debating whether this was a failed supernova, a direct collapse into a black hole, or something even stranger. Every new dataset Webb beams back brings us closer to solving the mystery, revealing a universe where stars don't just die. They vanish, leaving behind questions that challenge our understanding of physics itself. The telescope's infrared eyes are also probing the birthplaces of stars, regions like the Orion Nebula where dusty cocoons hide stellar nurseries. Here, Webb has spotted young stars flickering unpredictably, some dimming abruptly as if cloaked by vast clouds of debris. Could these be the early stages of stellar evaporation, with stars being smothered by their own birth clouds, or evidence of protoplanetary disks collapsing prematurely into black holes? Each observation blurs the line between star formation and destruction, suggesting the universe has more ways to erase its giants than we ever imagined. What's clear is this: Webb isn't just filling gaps in our knowledge, it's revealing a cosmos far more dynamic and mysterious than we dreamed. Every vanished star it documents, every distorted cluster it maps, forces us to rethink the life cycles of the universe's brightest objects. And with years of observations still ahead, the biggest revelations may yet be hiding in the darkness, waiting for Webb's infrared gaze to bring them into the light. Dark stars sound like something from a science fiction novel: celestial bodies, fueled not by the nuclear fires we know, but by the annihilation of dark matter itself. These hypothetical giants, if they existed, would defy everything we understand about stellar physics. Picture a star so massive it could dwarf our solar system, glowing not with visible light but with the faint heat of particles colliding in the shadows. According to some theories, the first stars in the universe might have been just like this, invisible behemoths powered by dark matter's mysterious energy, their light swallowed by their own strangeness. The idea hinges on dark matter's potential to interact with itself. While ordinary matter clumps into stars and galaxies, dark matter, making up 85% of the universe's mass, floats through space like a ghost, barely noticing the cosmos around it. But in the early universe, where dark matter was denser, particles might have collided and annihilated, releasing enough heat to ignite stars without nuclear fusion. These dark stars would have grown to staggering sizes, hundreds of times wider than our Sun, their cores churning with energy we can't see. And when they finally died, they wouldn't leave behind the familiar remnants, no white dwarfs, no neutron stars. Instead, they might have collapsed directly into black holes, seeding the cosmos with invisible traps from the very beginning, the most tantalizing clue. Some globular clusters, ancient collections of stars orbiting our galaxy, behave as if they're heavier than they appear. Their stars move too fast, their orbits too tight, as if something massive but unseen is tugging at them. Could dark stars be the missing piece? Their remnants, hidden in plain sight, might explain why certain clusters seem to dissolve faster than physics predicts. Unlike black holes formed from ordinary stars, these primordial relics could be far more common, lurking in the hearts of clusters and warping their evolution from within. Yet proving their existence is like trying to catch smoke with your hands. Dark stars, by definition, would emit almost no light, just a whisper of heat in the infrared spectrum. That's where telescopes like James Webb come in. By scanning the oldest, most distant corners of the universe, Webb might spot the faint thermal fingerprints of these shadowy giants, or their ghostly descendants hiding in modern clusters. Even a single detection would rewrite cosmic history, revealing a universe where the first stars weren't just different, they were something beyond our wildest imagination. The implications stretch far beyond stellar oddities. If dark stars existed, they could solve multiple cosmic mysteries at once. Their black hole remnants might account for the universe's missing supermassive black holes, which appear too early in cosmic history to have formed by ordinary means. Their influence could explain why some star clusters seem to evaporate unnaturally fast, their stars scattered by invisible anchors, and their very existence would mean dark matter isn't just a passive spectator. It's an active player in the story of the cosmos, shaping the universe in ways we're only beginning to guess. For now, dark stars remain a breathtaking what if. But in a universe full of vanishing acts and silent collapses, they're a reminder that the most profound truths might be hiding in the darkest corners, waiting for the right tools and the right minds to bring them into the light. Quantum mechanics might hold the key to the universe's quietest vanishing acts. At the heart of a collapsing star, where matter is crushed to densities beyond imagination, the usual rules of physics start to bend or break entirely. Picture a star so dense that a single teaspoon of its core would weigh more than Mount Everest. Under these extreme conditions, particles stop behaving like tiny marbles and start acting like waves, blurring together in a quantum haze where certainty dissolves into probability. Could this subatomic chaos rewrite the fate of dying stars, allowing them to slip away without the cosmic fanfare we expect? Take neutron stars as an example. These stellar corpses are so compact that their protons and electrons fuse into neutrons, creating a bizarre quantum fluid where particles move in lockstep, unaffected by friction. But what if something even stranger happens in the final moments of a collapsing star? Some theories suggest that at critical densities, quantum pressure, a force arising from the fundamental uncertainty of particle positions, might momentarily halt a collapse only to then fail catastrophically. The result, a star doesn't explode or implode smoothly, but instead flickers out of existence like a candle snuffed by an invisible hand. Then there's the speculative realm of quantum tunneling. In everyday life, particles can't pass through solid barriers, but in the quantum world, there's always a tiny chance they'll tunnel through anyway. Scale this up to a stellar core, and you get a wild possibility. A star's entire mass quantum tunneling into a black hole in an instant. No shockwave, no debris, just a sudden absence where a star once stood. It's as if the universe cheated, teleporting matter past the point of no return without the usual gravitational drama. The most mind-bending idea comes from quantum gravity, the still theoretical framework meant to unite Einstein's relativity with quantum mechanics. In this uncharted territory, space-time itself might become foamy at microscopic scales, riddled with virtual black holes that pop in and out of existence. If a collapsing star interacts with this quantum foam, it could fragment, its mass dispersed across dimensions we can't perceive. From our vantage point, the star wouldn't explode or collapse. It would simply dissolve like sugar in water, leaving no trace behind. Of course, these ideas push the limits of known physics. Unlike black holes or dark matter, quantum effects in stellar collapse lack direct observational evidence for now. But the gaps in our understanding are tantalizing. Why do some massive stars vanish without the gravitational wave signatures we'd expect from a traditional collapse? Could quantum fluctuations explain why certain supernova models fail to match real-world observations? Every unexplained disappearance nudges us closer to the edge of current theory, hinting that the universe's rulebook might have pages we haven't even glimpsed yet. The next generation of gravitational wave detectors, like the Einstein telescope, could change everything. By sensing ripples in space-time with unprecedented precision, they might catch the faint tremor of a star's core succumbing to quantum instability, a signature unlike any classical collapse. Until then, these quantum vanishing acts remain one of astrophysics' most provocative what-ifs. The stars we see blinking out in silence might not just be dying. They could be stepping through a door we didn't know existed, leaving us to piece together the clues they left behind. Primordial black holes could be the universe's oldest ghostly predators, tiny, ancient, and nearly invisible. Unlike the black holes we know today, formed from collapsing stars, these mysterious objects might have been forged in the chaos of the Big Bang itself. Picture the universe in its first frantic moments, a seething soup of energy and matter where quantum fluctuations could have compressed regions so dense they collapsed directly into black holes, some no larger than an atom, others as massive as a star. If they exist, these primordial relics could be drifting through space right now, hiding in the darkness between stars, occasionally crossing paths with unsuspecting clusters. The terrifying beauty of primordial black holes is their stealth. Without the glowing accretion disks of their larger cousins, they'd be nearly impossible to spot unless they fed. Imagine one the size of a mountain drifting into a star cluster. Too small to shred stars dramatically, it could instead siphon off their gas slowly, like a shadow draining color from a painting. Over millennia, stars near its path would dim and cool, their energy vanishing into an unseen maw. No explosion, no flare, just a gradual fading, as if the universe itself were erasing them. Some of the most compelling evidence for these ancient objects comes from gravitational microlensing surveys. When a massive object passes between us and a distant star, Its gravity bends the star's light, causing a brief brightening. Astronomers have spotted unexplained microlensing events that don't match any known celestial bodies, brief flashes with no visible source. Could these be primordial black holes drifting silently through our galaxy? Even more intriguing, their distribution might explain why some star clusters seem to dissolve faster than expected, their stars disappearing as if plucked by invisible fingers. The implications stretch far beyond missing stars. If primordial black holes are real, they could be the elusive dark matter we've been searching for. Their combined gravity might explain why galaxies rotate faster than visible matter alone can account for. Some theories even suggest these black holes could seed the growth of supermassive monsters at galactic centers, swallowing gas and stars until they balloon into the giants we observe today. Yet the hunt is fraught with challenges. A primordial black hole the mass of a planet wouldn't emit detectable Hawking radiation, and one too small would have evaporated by now. Their best chance of detection lies in subtle gravitational nudges, disturbances in star clusters, unexpected lensing events, or even ripples in the cosmic microwave background. Every unexplained gap in a cluster, every odd stellar orbit could be a clue. The most haunting possibility: these black holes might not just hide in space, they could be passing through Earth right now. Some models suggest a primordial black hole the size of a proton could zip through our planet, leaving behind faint seismic ripples or strange particle tracks in detectors. So far, no definitive signal has been found, but the search continues. If primordial black holes are out there, lurking in the dark, they'd rewrite not just the story of vanishing stars, but the entire history of the cosmos. The universe's oldest ghosts might have been hiding in plain sight all along, their silent feasts leaving gaps in the sky we're only now learning to see. Multi-messenger astronomy is like assembling a cosmic jigsaw puzzle, where light, gravitational waves, and even ghostly particles called neutrinos each reveal a piece of the bigger picture. Imagine trying to solve the mystery of vanishing star clusters with just one tool. It'd be like listening to an orchestra with only the violins turned up. You'd miss the depth, the layers, the full story. That's why scientists now combine forces, using telescopes to capture light, gravitational wave detectors to feel the tremors of colliding black holes, and neutrino observatories to catch the faint whispers of dying stars. Together, they're peeling back the curtain on the universe's most elusive acts. Take the case of a massive star collapsing silently into a black hole. A telescope might see its light flicker and fade, but without context, it's just another dimming dot. Add gravitational waves into the mix, though, and suddenly you've got proof of a violent implosion, ripples in space-time that betray the star's final moments. Neutrinos, those nearly massless particles that stream through solid rock like it's air, could carry even more clues. When a star's core collapses, it floods the cosmos with these tiny messengers, offering a real-time snapshot of the chaos unfolding inside. In 2018, the Neutrino Observatory ice cube detected a high-energy neutrino that, when traced back to its origin, pointed to a flaring black hole 4 billion light-years away. It was a watershed moment, proof that these particles could help pinpoint cosmic catastrophes invisible to traditional telescopes. But multi-messenger astronomy isn't just about catching events after they happen. It's about predicting them too. Gravitational wave detectors like LIGO and Virgo can sense the spiraling dance of black holes long before they collide, giving telescopes a heads-up to swing into position. In 2017, this synergy made history when a neutron-star merger sent out both gravitational waves and a gamma-ray burst. Telescopes worldwide captured the aftermath in every wavelength, from X-rays to radio waves, revealing how gold and platinum were forged in the explosion's wake. It was a Rosetta Stone moment, proving that the universe's most dramatic events speak in multiple languages at once. Now, apply that to vanishing star clusters. If a cluster's brightest stars are disappearing without a trace, gravitational waves might reveal the quiet mergers of black holes we never saw form. Neutrinos could hint at stars imploding in regions too dusty for light to escape. Even cosmic rays, high-energy particles from deep space, might carry fingerprints of dark matter interactions erasing stars from within. The challenge is timing. Unlike a neutron-star merger, which screams its presence across the cosmos, a silent collapse or a slow-motion cluster evaporation might only whisper. That's where next-generation tools come in. The Einstein telescope, with its unprecedented sensitivity, could catch gravitational waves from smaller, quieter black holes. The upcoming Vera-C Rubin Observatory will scan the entire visible sky every few nights, spotting subtle changes in clusters that older telescopes would miss. The promise of multi-messenger astronomy isn't just filling in gaps, it's rewriting the script. Every time we pair a gravitational wave with a neutrino or match a strange X-ray signal to a star's disappearance, we're learning that the universe doesn't play by single rules. A vanishing act might look like a failure from one angle but reveal a breathtaking new physics from another. And as our tools grow sharper, the biggest revelations might come from the signals we're only just learning to hear, the ones hiding in the quiet between the cosmic fireworks. The Fermi paradox asks a haunting question. If the universe is so vast, where is everyone? One possible answer lies not in the absence of life, but in its ambition. Imagine a civilization so advanced it doesn't just use planets for resources, but taps into stars themselves. Theoretically, an alien society harnessing a star's energy through hypothetical megastructures like Dyson spheres could cause it to dim or vanish from our telescopes. While this idea borders on science fiction, it's eerily consistent with the silent disappearances astronomers are now documenting. Take the case of Tabby's star, a distant sun that dimmed unpredictably, sparking debates about whether its light was being blocked by artificial constructs. Though natural explanations like dust clouds eventually prevailed, the episode revealed how easily a star's unnatural dimming could mimic cosmic phenomena. Now scale that up. If a civilization could dismantle or enclose an entire star cluster, the result would look like the unexplained voids we're finding. No explosions, no debris, just darkness where brilliance once blazed. Skeptics rightly point out the lack of direct evidence. If star-harvesting civilizations existed, wouldn't they leave traces, thermal waste, gravitational disturbances, or communication signals? Yet counterarguments suggest we might be missing subtle clues. A sufficiently advanced society could recycle energy with near-perfect efficiency, leaving minimal heat signatures. Or perhaps they've moved beyond electromagnetic communication, using neutrino beams or quantum entanglement channels we're only beginning to explore. The darker twist, such civilizations might not just hide stars, they could erase rivals. If harnessing a star's energy grants unimaginable power, the first species to achieve it might systematically dismantle nearby stars to prevent competition. This berserker hypothesis paints a grim solution to Fermi's paradox. The great silence isn't because life is rare, but because it's ruthlessly efficient at self-preservation. Of course, extraordinary claims demand extraordinary evidence. Most vanishing stars likely have natural explanations: direct collapse, dark matter interactions, or tidal disruptions. But the mere possibility that some disappearances could be artificial forces us to rethink our place in the cosmos. Every unexplained void is a Rorschach test, reflecting not just the universe's mysteries, but our own hopes and fears about what or who might be out there. The stars that vanish without a trace might be more than cosmic oddities. They could be footprints left by something we're not yet equipped to understand. Some stellar explosions are cosmic tricksters bright enough to catch our attention, yet too dim to fit the script. These so-called supernova imposters flare up with just a fraction of the energy of their full-blown cousins, burning out quickly like matches struck in a hurricane. Take SN 2008S, a star in the galaxy NGC 6946 that brightened dramatically, then fizzled within months, leaving astronomers scratching their heads. It wasn't the cataclysmic finale of a massive star, nor was it a typical stellar outburst. It was something in between, a cosmic charade that blurred the line between eruption and extinction. What makes these events so puzzling is their defiance of expectations. A true supernova should tear a star apart, scattering its guts across light years and leaving behind a glowing remnant. But imposters like SN 2008S seem to barely disrupt their host stars, as if the explosion got cold feet halfway through. One theory suggests these are failed supernova, in the making stars that try to explode but lack the oomph to finish the job. Instead of detonating, they might eject just their outer layers before their cores collapse silently into black holes, like a firework that sputters instead of bursting. Then there's the case of Eta Carinae, a volatile behemoth in our own galaxy that's been staging violent outbursts for centuries. In the 1840s, it brightened to nearly rival Sirius, then faded without a supernova. Modern observations reveal twin lobes of gas expelled during that event, now expanding slowly like a celestial hourglass. Eta Carinae isn't dead yet. It's a ticking time bomb, and its past eruptions might be dress rehearsals for a final act that never comes. Some researchers think it could become a supernova imposter on a grand scale, fizzling instead of exploding, leaving behind a black hole with no fanfare. The most haunting possibility, these imposters might be stars literally tearing themselves apart from the inside. In dense environments like globular clusters, stellar collisions or close encounters could trigger partial disruptions, explosions that rip off a star's outer layers but leave its core intact. The result would be a fleeting flash, just bright enough to mimic a supernova's first act before the curtain drops prematurely. It's a stellar magic trick where the disappearance is the real illusion, hiding the quiet collapse happening behind the scene. Every imposter we discover forces us to rethink the boundaries of stellar death. Maybe the universe has more ways for stars to bow out than we've imagined, not with a bang, not with a whimper, but with a cryptic shrug. And as telescopes grow sharper, these cosmic masquerades might finally reveal their true faces, showing us the hidden pathway stars take when they're ready to vanish from the stage. In the chaotic dance of a dense star cluster, the biggest stars don't just shine brighter, they feed on their neighbors. This isn't science fiction. It's a brutal reality called stellar cannibalism, where massive stars grow even larger by absorbing smaller companions, accelerating their own demise in the process. Picture a cosmic game of Pac-Man, where the largest stars gobble up others whole, their gravity stretching and tearing apart nearby stars until nothing remains but a swollen, unstable behemoth. The result, a star so massive it defies the usual rules of stellar death, collapsing silently into a black hole without the explosive finale we'd expect. Take the case of binary star systems in globular clusters like Omega Centauri. These tight-knit pairs orbit each other so closely that their outer atmospheres can touch, creating a bridge of gas between them. Over time, the more massive star siphons material from its smaller companion, growing heavier and more unstable. In extreme cases, the smaller star is entirely consumed, vanishing into its predator's core like a drop of ink in water. This process, known as mass transfer, can turn an already massive star into a true monster, one that burns through its fuel at a breakneck pace, hurtling toward collapse long before its time. But the real twist comes when these cannibal stars reach the end of their lives. Normally, a star's core collapse triggers a supernova, blasting its outer layers into space. But for stars that have gorged themselves on companions, the math changes. Their cores become so dense, so heavy, that the collapse doesn't rebound. It just keeps going, swallowing the star whole. No shockwave, no brilliant flash, just a sudden absence where a star once blazed. Astronomers call this a failed supernova, and it might explain why some of the universe's most massive stars vanish without a trace. The evidence is mounting. In clusters like the Arches near the center of our galaxy, stars are packed so tightly that collisions and mergers are inevitable. Infrared observations reveal stars with bizarre chemical signatures, elements like carbon and nitrogen, enriched to levels that only make sense if they've ingested other stars. These chemical fingerprints are the smoking guns of cosmic cannibalism, proof that stars don't just live and die in isolation. They're part of a violent, interconnected ecosystem where the strong literally consume the weak. And the consequences ripple far beyond individual stars. When a cannibal star collapses silently into a black hole, it leaves behind no debris to seed future generations of stars and planets. Heavy elements like gold and platinum, normally forged in supernova explosions, get locked away behind an event horizon, lost to the cosmos forever. Over time, this could alter the chemical makeup of entire galaxies, leaving them poorer in the building blocks of life. Yet the most unsettling thought is this: stellar cannibalism might be just one piece of a larger puzzle. Combine it with black hole mergers, dark matter interactions, and quantum collapses, and you get a universe where stars don't just die, they're erased, their stories rewritten by forces we're only beginning to understand. Every time a massive star vanishes without a trace, it's not just a mystery, it's a clue pointing us toward the hidden laws that govern the cosmos' darkest corners. Magnetic fields are the invisible architects of the cosmos, shaping the lives and deaths of stars in ways we're only beginning to understand. Picture a star's magnetic field as a cosmic spiderweb, woven through its layers of plasma, directing the flow of energy and matter with unseen force. Normally, these fields help stars maintain their structure, but in the most massive stars, they can become so intense they warp the very fabric of stellar death. When such a star reaches its final moments, its magnetic field might act like a straitjacket, binding the star's outer layers so tightly that the explosive rebound of a supernova is smothered before it can even begin. Instead of a brilliant explosion, the star's core collapses unimpeded, silently, swiftly, into a black hole. This isn't just theoretical. Take the case of magnetars, the universe's most magnetic objects. These neutron stars boast fields 1 trillion times stronger than Earth's, so powerful they could strip the data from a credit card halfway across the galaxy. If a star's magnetic field is even a fraction of that strength as it dies, it could drastically alter the collapse process. Simulations show that strong magnetic fields can channel a star's energy inward, like a cosmic feedback loop, preventing the shockwave of a supernova from ever reaching the surface. The result, a star that implodes without a sound, its light swallowed by its own magnetism. The fingerprints of this process might already be hiding in plain sight. Astronomers have spotted stars with bizarre chemical compositions, layers of elements like helium and nitrogen concentrated in ways that defy normal fusion patterns. These anomalies could be the scars of magnetic fields so strong they churn a star's interior like a blender, mixing layers that should remain separate. When such a star collapses, its twisted magnetic field might trap the explosion's energy entirely, leaving behind no trace but a black hole and a faint, fading ripple in space-time. The implications stretch far beyond individual stars. If magnetic suppression is common, it could explain why some star clusters seem to hemorrhage their most massive members at an unnatural rate. Clusters with high stellar densities where stars are packed shoulder to shoulder might foster stronger magnetic fields through collisions or close encounters, creating ideal conditions for silent collapses. Over time, this could leave clusters riddled with black holes, their brightest stars vanishing one by one, their departures marked only by the subtle warping of gravity. Yet the mystery deepens when we consider the outliers. Some vanishing stars don't fit the magnetic model, their fields too weak, their collapses too sudden. That's led scientists to suspect a cosmic collaboration, where magnetism teams up with other forces like rapid rotation or dark matter interactions to pull off the ultimate stellar disappearing act. The more we learn, the clearer it becomes. The universe doesn't just erase stars, it engineers their exits with a precision that humbles our understanding. And somewhere in that interplay of magnetism, gravity, and chaos lies the answer to why some of the cosmos' brightest lights vanish without a whisper. At the heart of every neutron star lies a mystery so profound it challenges the very laws of physics: what happens to matter when crushed beyond imagination. Under pressures 100 trillion times stronger than Earth's atmosphere, protons and electrons fuse into neutrons, creating a quantum soup so dense a sugar cube-sized chunk would weigh as much as a mountain. But what if nature has an even stranger recipe? Some theories suggest that under these extreme conditions, neutrons themselves might shatter into their fundamental components, quarks, giving birth to something far more exotic, a strange star. Unlike ordinary neutron stars, strange stars would be made primarily of strange quark matter, a hypothetical state where up, down, and strange quarks mingle freely without forming protons or neutrons. This substance, if it exists, would be unlike anything in our observable universe, more stable than iron, denser than neutronium, and potentially indestructible. A single strange star the size of Manhattan could outweigh our Sun, its surface smoother than polished glass, its gravitational pull so intense it warps light into glowing rings. Most chillingly, these objects might be nearly invisible, emitting little heat or radiation, camouflaged against the cosmic background like perfect black holes. The evidence for their existence is tantalizingly indirect. Some pulsars, rapidly spinning neutron stars, have masses and sizes that don't quite fit predictions, as if their interiors are made of something denser than neutrons. Then there's the case of X-ray bursts with abnormal energy signatures, events where compact objects seem to glitch in ways that defy neutron star models. Could these be strange stars revealing their true nature? Even more provocative are the theoretical calculations suggesting that a strange star's surface might occasionally crack, releasing quark nova, explosions 100 times brighter than supernovas, yet so rare we've possibly mistaken them for other cosmic cataclysms. But the real bombshell, strange stars might not just hide in plain sight, they could be actively erasing evidence of their origins. If a massive star collapses directly into a strange star instead of a black hole, the process would be eerily quiet. No supernova, no neutrino burst, just a star winking out as its core transforms into quark matter. Over time, entire clusters could dissolve this way, their brightest stars replaced by dark, quark-bound remnants. When these exotic objects merge, as gravitational wave detectors like LIGO have observed, they might produce signals subtly different from neutron star collisions. hints lurking in data we're only now learning to decode. The implications rewrite cosmic history. If strange stars exist, they could be the universe's ultimate cosmic camouflage, masquerading as neutron stars while hiding the truth that matter under sufficient pressure becomes something entirely alien. They might explain why some star clusters seem to lose massive stars without fireworks, or why certain supernova models fail to match observations. Most unsettlingly, they could be far more common than we think, an invisible population of quark-bound relics, rewriting the rules of stellar evolution from the shadows. Every unexplained gap in a star cluster, every anomalous pulsar glitch, every bizarre gravitational wave signal could be a breadcrumb leading to this revelation, that the universe's most enduring mysteries might be written in quarks, not stars. And the only way to read them is to keep looking not just for what shines, but for what hides in plain sight. Imagine watching a star's final moments, except those moments stretch into centuries, millennia, even eons. This isn't science fiction, it's the mind-bending reality of time dilation near black holes. When a massive star collapses into one of these gravitational monsters, the extreme warping of space-time doesn't just trap light, it twists time itself. From our vantage point, far removed from the black hole's crushing grip, the star's death might appear instantaneous. But for the star itself, or any hypothetical observer foolish enough to hover near the event horizon, time slows to a crawl. A single second for the doomed star could equate to thousands of years for the rest of the universe. This bizarre effect stems from Einstein's theory of general relativity, which revealed that gravity doesn't just bend space, it stretches time. The stronger the gravitational pull, the more time slows down. Near a black hole where gravity is so intense that not even light can escape, time dilation reaches extremes that defy intuition. Picture an astronaut falling toward the event horizon. To distant observers, their descent would seem to slow, then freeze entirely as their image reddens and fades, a phenomenon called gravitational redshift. The astronaut's last visible moments would smear across eternity, their watch ticking infinitely slowly from our perspective, even as they themselves plunge into oblivion in what feels like mere seconds. Now apply this to vanishing stars. If a massive star collapses directly into a black hole, its final flickers of light photons struggling to escape the growing gravitational well would be stretched to longer, redder wavelengths. The star's last gasp, as seen from Earth, might appear as a gradual dimming rather than a sudden disappearance. But here's the twist: if the collapse is rapid enough, time dilation near the newborn black hole could compress the star's death throes into an observational blink. What looks like an instant vanishing act to us might, from the star's doomed perspective, unfold over agonizing epochs. This time-warping effect could explain why some stars seem to vanish without a trace. Telescopes monitoring distant clusters might miss the star's drawn-out demise entirely, catching only the before and after with nothing in between. It's like flipping a light switch in a room where the bulb takes centuries to dim. By the time you notice the change, the room has been dark for ages. Yet time dilation isn't the only factor at play. The star's own light, redshifted beyond detection, might fade into the cosmic background, invisible to our instruments. Combine this with the black hole's appetite for swallowing any debris, and you have the perfect recipe for a cosmic disappearing act. No explosion, no lingering glow, just a star's light stretched and smeared into nothingness. The universe, it seems, doesn't just erase stars, it edits them out of existence frame by frame, in a slow-motion deletion we're only beginning to perceive. Cosmic dust doesn't just drift idly through space, it's the ultimate cosmic magician's curtain, hiding stellar deaths in plain sight. Picture a massive star reaching the end of its life, ready to explode in a supernova or collapse into a black hole. But instead of a dramatic farewell, its light is swallowed by vast clouds of dust and gas, thick enough to block even the brightest stellar fireworks. To telescopes scanning the sky in visible light, it's as if the star never existed, vanishing without leaving behind so much as a flicker. This isn't hypothetical. Take the case of the star N6946 BH1, a red supergiant in the fireworks galaxy that simply faded from view. Initial observations suggested it had collapsed directly into a black hole, but follow-up studies revealed a different story. Infrared telescopes, which see through dust by detecting heat rather than visible light, caught a faint glow lingering where the star once shone. The verdict: the star did explode, but the blast was muffled by a shroud of dust so dense that only a fraction of its light escaped. What looked like a silent collapse was actually a cosmic spectacle smothered under layers of interstellar debris. The implications are profound. If dust can hide supernovas, it could be masking countless stellar deaths across the universe. Regions like the Pillars of Creation or the Orion Molecular Cloud Complex are teeming with star-forming dust so thick that even the most violent stellar explosions might go unnoticed. Infrared astronomy becomes the key to piercing these veils, revealing the heat signatures of dying stars that optical telescopes miss. The Spitzer Space Telescope, for example, has uncovered dozens of hidden supernovas in dusty galaxies, their light absorbed and re-emitted as infrared radiation, a cosmic game of hide and seek where heat betrays what darkness conceals. But dust doesn't just obscure, it distorts. When a star's light passes through dense dust clouds, it doesn't just dim, it scatters, reddening like the sun at sunset. This phenomenon, called interstellar reddening, can make a dying star appear cooler and fainter than it truly is, tricking astronomers into misjudging its fate. Some vanishing stars might not be collapsing silently at all. They could be exploding behind dust curtains, their light so stretched and diluted that they mimic the gradual fade of a failed supernova. The challenge is separating dust's illusions from genuine cosmic mysteries. Advanced instruments like the James Webb Space Telescope are revolutionizing this hunt, combining infrared vision with unprecedented sensitivity to peer into the universe's dustiest corners. Already, Webb has spotted stars in the process of being born and dying within the same nebula, revealing how closely linked creation and destruction really are. Every dusty veil it lifts forces us to reconsider the stories we've told about stellar life cycles, and the possibility that some of the universe's most dramatic exits are playing out unseen, waiting for the right tools to bring them into the light. Yet even infrared has its limits. The dustiest regions of space, like the hearts of starburst galaxies, may absorb so much energy that not even heat escapes. In these extremes, stars could vanish entirely, their deaths recorded only in the gravitational ripples they leave behind, or not at all. The universe's greatest disappearing acts might not just defy our expectations. They could be hiding in the one place we're only beginning to explore, the silent, dusty dark. Binary star systems rewrite the rules of stellar disappearance because sometimes a star doesn't just vanish on its own. It gets eaten. Picture two massive stars locked in a gravitational dance, orbiting so closely they could fit inside our solar system. When one reaches the end of its life, collapsing into a black hole, the balance of this cosmic tango shifts violently. The newborn black hole, now a silent predator, begins siphoning gas from its living companion. But here's the twist. If the feast is slow and steady, there might be no dramatic flare, no X-ray burst to alert telescopes, just a star fading quietly, its light dimming as it's consumed bite by bite, until nothing remains but an invisible black hole and an empty stretch of sky. Take the system LB1, discovered in 2019. Astronomers initially thought they'd found a 70 solar mass black hole, impossible under standard stellar evolution models. The truth was even stranger. LB1's black hole wasn't born alone. It was part of a binary pair, its companion star mysteriously stripped of outer layers. The best explanation: the black hole had been feeding on its neighbor for millions of years, its meal so gradual it left almost no trace. Systems like this could be hiding in plain sight across the galaxy, their missing stars written off as observational errors or cosmic glitches. The process isn't always gentle. In some binaries, the black hole's gravity distorts its companion into a teardrop shape, pulling material into a swirling accretion disk that glows in X-rays. But even these bright signatures fade over time. As the donor star is depleted, the disk thins, the X-rays dim, and the system becomes virtually undetectable. By the time telescopes catch on, the star might already be gone, its absence masked by the black hole's event horizon, a cosmic crime scene with no visible evidence. Globular clusters packed with ancient stars are prime hunting grounds for these silent predators. In dense environments like Omega Centauri, binary systems are common, and close encounters can tighten their orbits, hastening the inevitable. Simulations show that black holes in these clusters often pair with massive stars, creating ticking time bombs. Over eons, the star is consumed, its matter funneled into the black hole with barely a ripple in the fabric of visible light. The result, a cluster that appears to lose its brightest members without explanation, their disappearances chalked up to evaporation or ejection when in reality, they've been swallowed whole. Yet the most unsettling implication lies in the numbers. If even a fraction of binary systems end this way, it means black holes could be far more numerous than we've accounted for, lurking in systems we've already catalogued, their presence betrayed only by the slow, methodical erasure of their partners. Every missing star in a binary-rich cluster might not be missing at all. It might just be hiding in the dark, behind an event horizon we've yet to learn how to see. The next generation of telescopes isn't just improving our view of the cosmos, it's rewriting the playbook on how we hunt for vanishing stars. Take the Vera Rubin Observatory, slated to begin its legacy survey of space and time in 2025. This ground-based powerhouse will scan the entire southern sky every few nights, catching subtle changes in star clusters that older telescopes would miss. Imagine spotting a massive star dimming erratically over weeks, then disappearing entirely, a telltale sign of a silent collapse into a black hole. With its ability to detect faint, fast-changing objects, Rubin could uncover dozens of these events yearly, turning what was once speculation into hard statistics. But Rubin's wide-field vision is only part of the puzzle. The European Space Agency's LISA mission, launching in the 2030s, will listen for gravitational waves at frequencies too low for ground-based detectors like LIGO. This opens a window into slower, quieter mergers, the kind that might occur when intermediate mass black holes swallow stars whole. Picture catching the faint ripple of a star's core collapsing directly into a black hole, an event too subtle to produce light but vibrating the fabric of space-time itself. LISA sensitivity could reveal black holes forming in real time, hidden deep within star clusters where optical telescopes see nothing amiss. Then there's the Nancy Grace Roman Space Telescope, NASA infrared marvel set to launch by 2027. While Hubble and Webb focus on deep but narrow fields, Roman will combine infrared vision with a panoramic view, perfect for spotting stars that vanish behind cosmic dust curtains. Its coronagraph instrument will even block starlight to hunt for dim companions like rogue black holes or dark matter clumps, orbiting visible stars. If strange gravitational tugs are destabilizing clusters, Roman might catch their fingerprints. And let's not forget the Einstein telescope, a future underground observatory designed to detect gravitational waves with 10 times LIGO precision. Buried to eliminate seismic noise, it could hear the faintest whispers of quantum collapses or primordial black holes merging in distant clusters. These signals might carry echoes of exotic physics, hints that stars aren't just vanishing but transforming into something beyond our current theories. The most exciting prospect: these missions won't work in isolation. Imagine Rubin spotting a star cluster dimming unexpectedly, Roman confirming the absence of dust or debris, and Lisa picking up a gravitational wave from the same region days later. This multi-messenger approach could finally piece together the full story of stellar disappearance, revealing whether black holes, dark matter, or something entirely new is at work. Yet the biggest revelations might come from surprises, anomalies these instruments weren't even designed to find. Every time we've built a better telescope, we've stumbled upon phenomena that upend our understanding. As these new eyes and ears turn toward the cosmos, one thing's certain: the universe's quietest vanishing acts won't stay hidden forever. And when the truth emerges, it might be stranger than anything we've dared to imagine.